All right, folks, let's take a look at some examples. This is going to be a little video on log derivatives and logarithmic differentiation. And you might be asking yourself, what's the difference between using log derivatives and logarithmic differentiation? And the answer to that is, hang out, dude. Dumbledore dies, man. Don't spoil the secret ending for everybody. I'll show you. Pacing. Log derivatives are just derivatives that involve logarithms. So let's get started here. There's a couple of things I want to say. There are two ways to go about any log derivative. And for the most part, you more or less can choose either route. So option one, direct calculation. What do I mean by that? Well, the derivative with respect to x of the natural log of 2x is equal to, according to our derivative rules, 1 over the inside times the derivative of the inside. And in this particular case, we just get 1 over 2x times 2. And the 2's cancel, and we're left with 1 over x. And that looks suspiciously like the derivative of just the natural log of x. So, is the derivative of the natural log of 2x and the derivative of the natural log of x exactly the same thing? And the answer to that is yes, and I'll show you why. Option 2, using log rules first. So, the derivative with respect to x of the natural log of 2x, well, this is a product, which means that this is the derivative with respect to x of the natural log of 2 plus the natural log of x, if you know your log rules. And this happens to be a constant. And we all know what the derivative of a constant is. This can be broken up, as the derivative with respect to x of the natural log of 2 plus the derivative with respect to x of the natural log of x, which is 0 plus 1 over x, which is just 1 over x. And there you have it. The same result. Okay. Either way is fine. And you might be thinking to yourself, well, if I can do it either way, I'll just do it the first way every single time. Okay, that's great. Knock yourself out. Now, example B here. We can do this one of two ways. We can either do option 1 again, in which case the derivative with respect to x of the natural log of x squared is equal to 1 over the inside times the derivative of the inside, which is equal to 1 over x squared times 2x, which is equal to 2x over x squared. There it is, that f prime over f form. And we'll get 1 power of x to cancel out, and this will be 1 over 2x. Now, I guess I should have called this option 1, not option. Option 1. Option 2. The derivative with respect to x of the natural log of x squared. Well, in this case, this is an exponent, and we can use the power rule for logarithms to rewrite this first. This is the derivative with respect to x of 2 times the natural log of x, which is just 2 times 1 over x. And so again, we can see same result. Now, for C here, we have to be really careful. First of all, we can't noob out. We need to note that the natural log squared of x is not the same thing as the natural log of x squared. We cannot use a power rule. Well, we can use a power rule, but not the logarithmic power rule. This is the natural log of x quantity squared. So you need to be careful with this notation and make sure you rewrite it in a way that is comfortable for you. That is to say, this is the derivative with respect to x of the natural log of x quantity squared. And in this case, we cannot use log rules to bring the 2 down as a coefficient. I hope you're paying attention, because I'm about to bring the 2 down. But I'm not about to bring the 2 down using log rules. I'm about to just take the derivative. And this is the chain rule. This is 2 times the natural log of x to the first power times the derivative with respect to x of the natural log of x. This 2 is from the derivative of the outside of the function, and this is from the chain rule times the derivative of the inside. So what am I getting at? Be careful. I wanted to show you these two in contrast to one another, specifically option 2 here versus example C. In option 2, I brought down the 2 as a coefficient before I took the derivative. So this is bring down the 2 as a coefficient using log power rule before the derivative. This is from the derivative itself. So do not confuse the two. And students that do not pay attention to details and do not know the log rules really well get very confused in this section because they don't put in the time to understand what is basically the difference between the power rule for derivatives versus the power rule for logarithms. And they can look very similar. So consider yourself warned, man. And it's best, I think, if you rewrite things in this form so that you can go, oh yeah, aha, I'm using the chain rule and I'm bringing down the 2 as a derivative, not necessarily as a coefficient from the logarithm. Now to finish this up, this is 2 times, let me change the color here. 2 times the natural log of x times the derivative, which is 1 over x, and this is 2 natural log of x over x. That's our derivative here. Okay. Now, this next example, example D, is designed to teach you a lesson, so pay attention. People that skip this video and do not pay attention to this particular example are going to lose points, not because they're doing the problem wrong, but because it's a headache if you do not set the stage for doing this correctly. So, option 1, direct calculation. I see it over and over again with students. They barely learn the derivative for logarithms. They memorize that one basic rule and they think it's going to solve all their problems. And then algebra rears its ugly head and rips your heart out of your beating chest. So be careful, dude. Direct calculation. This is the quote-unquote f of x. And so the derivative here, this nasty bit of work, is 1 over the inside times the derivative of the inside. Ugh. So now we're dealing with a reciprocal here. Let's see, this is x squared minus 1 over the square root of x. And now this is the chain, or the quotient rule even. In fact, now I'm going to rewrite this as x to the 1/2. And so this is going to be low d high minus high d low over the denominator squared, bro. And then we'll keep cleaning this up. This is x squared minus 1 over the square root of x times this monstrosity. X squared minus 1 times 1 over 2 root x. Let me not write it that way. That's going to freak people out. 1/2 x to the negative 1/2 minus x to the 1/2 times the derivative over here, which is, that's a hard one, 2x over, let's see, x squared minus 1 squared. I'm going to give you a bit of advice. If you're going to do it this way, and you shouldn't even be doing it this way, don't you dare multiply that out. Do not foil this. It will make you very unhappy. Especially since you have a factor of it right here that will cancel. And then you clean this up a little bit and, let's see here. Do you guys know how to factor? I mean, really? Do you know how to factor? Really? Let's see. We have x squared minus 1 over the square root of x. And then what do I have in common here? Let's see. Let's change colors. What I do have is I have some factors of x in common, and I'm going to factor out the lesser of the two powers. So when I factor out an x to the 1/2, negative 1/2, I'm going to be left with x squared minus 1 times 1/2. I probably should have pulled out that half too. Let's do that like a boss. Here we go. I'm going to pull out. If you can't follow this, don't worry. You shouldn't really be doing it this way anyway. But this is called algebra. We're going to pull out a 1/2 x to the negative 1/2. We're going to be left with x squared minus 1. And then this is going to be minus 2 because I pulled out the 1/2. I'm going to have to double that guy. And then if I factor out an x to the negative 1/2, this is going to become x to the positive 1 times another 2x all over x squared minus 1 squared. And if you really want to know how I did that in detail, you should come to office hours, and I'll show you. Okay, so let's see. Ooh, that's another root x in the denominator. That's going to jive nicely with that one. And I'm going to get some cancellation here with at least one factor of this x squared minus 1. So let's see, and then this is x squared minus 1 minus 4x squared, which is really a negative 3x squared minus 1, something like that. And this will become, if I'm not mistaken, and I've been known to be mistaken, negative 3x squared minus 1 divided by, let's see, what do I got in the denominator? I got a 2. I got one factor of x squared minus 1, and this root x and this root x are going to combine together to give me one factor of root x. And so the answer here is negative 3x squared minus 1 divided by 2x times x squared minus 1. And at that point, I guess you could multiply out that denominator if you wanted to. Now, let's talk about why you shouldn't have done this problem that way to begin with. Let's make some room here. Come on. No, stop it. Okay. Option 2. The derivative with respect to x of the natural log of the square root of x over x squared minus 1 is equal to the derivative with respect to x of the natural log of x to the 1/2 divided by x plus 1, x minus 1. And if I use log rules, that's the derivative of 1/2 the natural log of x minus the natural log of x plus 1 minus the natural log of x minus 1. And then when I take the derivative, this is just 1/2 times 1 over x minus 1 over x plus 1, 1 over the inside, times the derivative of the inside, minus 1 over the inside, times the derivative of the inside. Holy crap, did you just do that in 30 seconds, Jenkins? Probably less than that, to tell you the truth. And you might be saying to yourself, well, that doesn't look anything like the other answer you got. I know, because I didn't get a common denominator. You want to get a common denominator? Here you go. This is going to need an x plus 1, x minus 1 top and bottom. Oh, I'm going to run out of room if I don't do this correctly here. Here you go. This isn't strictly necessary. This is just for your benefit. So pay attention. X plus 1, x minus 1, x plus 1, x minus 1, minus 1 over x plus 1 times 2x over 2x times x minus 1 over x minus 1. I'm running out of room here. Minus 1 over x minus 1 times 2x over 2x times x plus 1 over x plus 1. And if you multiply all that garbage out, it's going to be one giant fraction over the denominator 2x times x plus 1 times x minus 1. And that's going to be x squared minus 1 minus 2x times x minus 1 minus 2x times x plus 1. And what you're going to get is negative 3x squared minus 1 over 2x times x squared minus 1. Now, none of that was strictly necessary. I would have stopped here. I just wanted to show you that this is the same result. And by using these log properties in the beginning, I just avoided this massive headache over here of product rule, quotient rule, chain rule, power rule. It just wipes everything out. So hopefully you can see the benefit there. This is the preferred method. Elegance. Direct calculation. We're going to call this brute force. Way to go, Kong. Calculus. Me like calculus. Good stuff. Okay. Tone it down a little bit, buddy. You're scaring the locals. Okay. Now, finally, in example 2 here, let's talk about what logarithmic differentiation is. If you'll notice in this problem, f of x equals the cube root of x squared minus x divided by e to the x sine squared x. I'm asked to find f prime of x. And I can just, again, use brute force. Or I can take this expression. Come on, duplicate it. I can take this expression and I can take the natural log of both sides, which will allow me to rewrite this as 1/3 the natural log of x squared minus x over e to the x times sine squared x, where I rewrote the radical cube root as a 1/3 power and brought it down as a coefficient. And then I can break this up even further as 1/3 times the quantity, the natural log of x squared minus x, minus the natural log of e to the x times sine squared x, which is 1/3 the natural log of, don't forget that this is x times x minus 1. I can rewrite that as the natural log of x plus the natural log of x minus 1. I can break this product up as the natural log of e to the x minus the natural log of sine squared x. And I know you're thinking to yourself, Jenkins, that was a product. Shouldn't this be negative or positive? Yeah, it should be, but I also distributed this negative sign. All right, so that's going to become negative when you distribute it. And then I can rewrite this as 1/3 the natural log of x plus 1/3 the natural log of x minus 1. Did you know that the natural log of e to the x is just x? And this becomes x over 3, negative. And then I can bring this 2 down as a coefficient and make this negative 2/3 the natural log of the sine of x. Now, don't put that on the fridge just yet because you haven't taken the derivative. This is what the natural log of f of x is equal to. Move that out of the way. So, now what we're going to do is we're going to take the derivative of both sides. So, the derivative of the natural log of f of x is equal to the derivative of 1/3 the natural log of x plus 1/3 the natural log of x minus 1 minus 1/3 x minus 2/3 the natural log of the sine of x. Taking the derivative of both sides on the left side, I get f prime of x divided by f of x. That's the natural log rule. On the right side, I'm just taking a bunch of derivatives. This is 1/3 times 1 over x plus 1/3 times 1 over x minus 1 times the derivative of that inside, which is just 1, minus 1/3 minus 2/3 times 1 over the sine of x. And the derivative of the sine of x is negative cosine x. And cleaning this up, we have 1 over 3x plus 1 over 3x minus 3 minus 1/3 plus 2/3 times the cotangent of x. And if we want to solve for f prime of x, all we have to do is multiply both sides by the denominator. So f prime of x is f of x times 1 over 3x plus 1 over 3x minus 3 minus 1/3 plus 2/3 times the cotangent of x, where f of x was this monstrosity. So my actual answer is, the derivative is the cube root of x squared minus x over e to the x times sine squared x times all this mess. 1 over 3x plus 1 over 3x minus 3 minus 1/3 plus 2/3 times, the cotangent of x. And that's my derivative. Now, as long-winded as that was, let's go back and reflect a little bit. That was a lot better than using the chain rule, the quotient rule, the product rule, the chain rule in order correctly. There's a lot going on with that derivative, and we're able to skirt all those problems by introducing a natural log and using log properties to break up our function before we even take the derivative. So that's what we did here. Use log properties to break up the function into bits before taking the derivative. Well, how is that any different than what we did up above? Right? If we look at some of these previous examples, isn't that what we just did right here? Yes and no. The difference between what we did up here and what we did down here was, in example 1, there was already a natural log in the problem. In this problem, we introduced our own natural log on both sides of the equation that allowed us to use log properties. So, step 1, take the natural log of both sides. And then step 2, use log properties before taking the derivative. And then step 3, differentiate and solve for f prime of x. Okay. One more example. This one is non-standard base for both the exponential and the logarithm. This is first and foremost a product. So let's get down. F prime of x is equal to the derivative of the first factor times the second factor plus, leaving the first factor alone, we take the derivative of the second factor and multiply. Okay, so this is a non-standard base for an exponential. The derivative of an exponential is itself times the derivative of the exponent times the natural log of the base. So everything in square brackets there is the derivative. And then I'll just multiply by log of 3x squared. Then plus 2 raised to the sine x power. I'm going to take the derivative of log of 3x squared. Now, this argument isn't so complicated that I got to use log rules to break it up. It's not that bad. But what is different here is this is not base e, it's base 10. So the derivative of the logarithm is 1 over the inside times the derivative of the inside. That's easy enough, I'll just do that. Times the derivative of the inside, and then divided by the natural log of the base. So cleaning this up, it's a monstrosity. Let's see, maybe we have all these natural logs in here. Maybe we should rewrite this using a change of base formula. Let's do that, actually. This is the natural log of 3x squared over the natural log of 10, which means that both terms have that as a common factor. So let's factor that out. This is 1 over the natural log of 10 times the quantity, let's see, negative natural log of 2 times the cosine of x times 2 to the sine x power. Oh, you know what? They both have a 2 sine x as well. Let's clean this up even more. What else do they have in common? Let's see, we got a natural log of 2 in common. No, not a natural log of 2. We got a 2 sine x in common. And we have that log base 10 in common. So let's pull that out. Oh, Jenkins, you're so ill-prepared. 2 sine x over the natural log of 10 times the quantity. Let's see, this one's negative, so I'll write that on the back end. Let's write that as minus cosine x times the natural log of 2 times the natural log of 3x squared. And this will clean up really nice. The x's will cancel, and we'll get some cancellation with the 6 and the 3, and we'll just get 2 over x. I kind of overestimated how much room I was going to need for that. Bang. And then this can be combined even more because we can combine these logs. This is no, we can't. That's not a sum. Never mind. We're not going to combine those logs. I'm jibber-jabbing. It is very late when I'm recording this, so you'll excuse my mental lapse. At any rate, let's see. This is... Now I'm just rewriting what I already have, making this video longer. 2 to the sine x power over the natural log of 10 times 2 over x minus cosine x times the natural log of 2 times the natural log of 3x squared. Gross. Ew. But that's the answer. All right, folks, this video is long enough. We're going to have one more video with some integration examples.